Hello and welcome to the module on Inventory Dynamics. In this module, we are going to understand how inventory changes over time and hopefully be able to visualize the dynamic behavior of inventory using graphs. Now, let's start by trying to see what happens to inventory in a typical store. Suppose initially we have a stock of some inventory. In this figure, it shows we have some 6 boxes of inventory. This is called as initial stock. Suppose on day 1, the shop faces a demand of 2 units. That means 2 units from the inventory is going to be sold against the demand that was received at the store, and the balance will have 4 cartons of inventory on day 1. Now, it's important to see when we are accounting for the inventory. Inventory is typically an end of the day value. That is, you can imagine when a shop is about to close, then they count how much inventory is the balance and then they record it as the inventory at end of period T or end of day T. And customer demand is assumed to occur throughout the day continuously over time. Now, on day 2, suppose the demand was additional 3 units. Those 3 units were sold on day 2. The balance is 1 carton that is shown. But suppose the shop also received 7 units. You can imagine that the 7 units was received just before the shop closed. So we use 3 units during the day and then we received additional 7 units at the end of the day, and then the inventory was accounted for, and we have a total of 8 units in the inventory at the end of day 2. On day 3, the demand was 5, so sales here was also 5, and there is a balance of 3 units in the inventory. And suppose on day 4, again the demand was 5, but now we don't have 5 units in the inventory, we have only 3 units. That means our sales could be only 3 units. And the 2 units of demand is deemed unfulfilled. This can be referred to as the demand being backordered or lost, as the case may be. But this is kind of cumbersome to draw boxes and represent it. So we would like to convert this into a graph. We can simply do by removing the boxes, and we already have the level indicators of circles. We can just draw the y-axis and x-axis. So y-axis is always inventory and x-axis is your time. And we simply connect the inventory changes over time. Although the inventory is recorded at discrete points in time at the end of day 0, day 1, day 2 and accounting happens, we assume that whenever demand is occurring continuously, so the inventory level will also change since demand occurs during the day. So your slope of this line is nothing but your negative of the demand rate. So again, this graph here shows only the physical inventory, and it reaches a value of 0 at day 4, and we still have 2 units of demand unfulfilled. If we want to account that can be shown as either a negative inventory or can be shown as a separate graph. Now, let's again take a slightly different view of what happened to the inventory. The figure on the right shows inventory in a box. So you can represent this as a physical inventory within the warehouse, which is shown by the rectangle. So this inventory is affected by sales and the received products. As you know, when sales occurs, the inventory is going to go down, and when the received products or new products are received, the inventory is going to increase. In turn, you can see that the sales is also affected by the demand, and there is another arrow connecting inventory to the sales. So this means that this actual sales value will be a function of demand as well as inventory. The minimum of the two is usually considered as the sales. And this quantity that is ordered will be received later. So that is what is indicated by this order quantity variable. That is one of the key decision variable in our inventory management. Inventory management. Yeah. So, so you can see the inventory is a key variable which is directly affected by the sales and received products, but there are other related variables which affects them, like the demand, quantity ordered, back ordered, lost sales, lead time, etc. Remember, all these variables continuously change over time, but these changes are triggered by specific discrete events such as receipt of new orders or the arrival of customer demands within the shop, the actual sales event, etc. Now, let us construct a few behavior over time graphs of inventory for some special cases so that we can better understand some of the terminologies and be able to better visualize what happens to the inventory. Let's take a very straightforward scenario. So I request you to imagine a warehouse where inventory is kept. Demand occurs at a known constant rate and demand is fulfilled from the inventory if it's available, and new goods are received adds to this inventory. Quite a straightforward assumptions, and assume a single product. Let's take up a more basic model with instantaneous resupply L equal to 0. That means whatever quantity we order, say Q of T be the quantity ordered, is delivered immediately. Let's draw some hypothetical example. So here on y-axis we have inventory, and the inventory keeps reducing, and being the shop, I don't want the inventory to go as soon as hits 0. I know that the lead time is 0, right? So whatever I order will come immediately. So at time period 5, I order some quantity which gets instantaneously delivered in time period 5. Similarly, I ordered in time period 11, time period 15 in this example. Also, since the demand is constant, that means the slope for all these cases is going to be exactly the same. The slope is constant, and that means demand is constant. The quantity ordered is strictly greater than 0 only in time period 5, 11 and 15. In all other periods, no ordering happens. We don't order anything in time period 1, time period 2, etc. Demand occurs and inventory reduces because of the demand. No new material comes. Only in time period 5 I order, and time period 5 I receive the material. So that's what this graph illustrates. But note that in this example, the quantity ordered is different in each of these periods. In time period 5 it is large, time period 11 it is smaller, 15 is little more than time period 11. This Q of T will be a key decision variable for inventory, which covers both timing as well as quantity. The T denotes when to be ordered, and Q denotes what is the quantity that is to be ordered at that time T. So this will be a key decision variable throughout our inventory management module. It's quite straightforward to kind of imagine that suppose order quantity is known and constant and resupply is fixed L, there is really no need for us to order different quantities when we need it. So ordering a constant quantity Q when I of T hits 0 is kind of an optimum configuration, and there is method through which we can choose this optimum quantity of Q or Q star so that it minimizes the total cost. Then we can get this classical sawtooth graph of inventory. So this is a classical way in which inventory graphs are represented. Let's introduce a new term. So the duration for which your quantity Q that you ordered actually lasts until you need to order again is called a cycle length or order cycle length. So that is a duration for which your quantity that you ordered or you received lasts until the next order is issued. So that is called as a cycle length denoted by capital T. Now let's try with some variants. Now let's relax one assumption. Suppose there is a constant and a finite lead time L. That means your ordering is not your order fulfillment is not instantaneous. Whatever your order comes after some fixed lead time L. Now if you see in the graph looks exactly the same. That's because when the demand rate is constant, it is quite intuitive for us to order a constant quantity Q some L periods before I of t hits 0. For example, in this graph, let us assume the lead time is 2 time periods. So that means I know that the material is going to go 0 at time period 5. So that means I need to order at time period 3, which will get delivered at time period 5. Quite straightforward, right? So that's exactly what we will do. We order Q units in time period 3, 8, 13 and 18, which gets delivered 2 periods later. So that they just arrive just as your inventory goes to 0. Thus we can avoid stock out. Stock out means a scenario where a demand occurs but you don't have material in your inventory to fulfill it. Now, but if you recall the graph shown here versus the graph shown when instantaneous resupply was there when L equal to 0, is exactly the same. So just by looking at this graph, we don't know the impact of this lead time. The best way to visualize it is to draw another graph of goods in transit. If you see the goods in transit, in time period 3, the full quantity that is ordered now starts moving and it takes 2 time periods until it actually reaches in time period 5, and once delivered, now there is no more goods in transit, and again when order is issued at time 8, then again that much quantity gets starts moving and reaches 2 time periods later at time period 10 when again it falls. So there you have an inventory in the top which is sawtooth shaped, and you have goods in transit which looks like a rectangular pulse function over time. Let's now introduce a few other terminologies. Let's begin with this specific terminology on backorder. Now we are again going to assume that the demand is constant. Lead time is also constant and finite. And we are going to order a fixed Q quantities in all the time periods, and there is something called as backorder. Just to imagine that, let us take this scenario where in the first time period, at the initial stock we had of say 10 units, but we forgot to order in time period 3. So on time period 5, when the inventory hit 0, we realized, and then we placed the first order in time period 5. We know that once I place an order, it takes a finite lead time of 2. That's again for this example, and that is going to come in only in time period 7. So let's assume a fixed Q dash units is ordered in time period 5, and again the same units is ordered now 8, 13 and 15. After the first mistake I did, that is only in 5 I ordered, I received at 7, but since then I became wise. I realized that the lead time was 2, so I ordered well in advance so that in future time periods the material is received exactly when inventory reaches 0, that is in time 10, 15 and 20 respectively. Now, but if you see the graph, you can see the graph which is going below 0. The inventory level graph is going below 0. That is one classical way to represent backlogs or back orders. So that negative inventory is used to represent backlogs or back orders. What back order means is that whatever the demand was faced when we didn't have inventory has to be fulfilled when the inventory became available. So you can imagine a local store where you ordered something, it was not there, So, but the customer was willing to wait. So after a day, whatever was ordered was supplied to the customer as soon as the new inventory came. So this is called as back order. Although the height of the graph is different, observe that the quantity Q, the time at which the inventory position before the goods was received or the inventory position after the goods was received is exactly the same. So from this point to this point, and in time period 10, inventory is 0, it went all the way to Q star, and again at time 15 it went from 0 to all the way to Q star, but in time period 7 it went from this point here to this point here, but the height is exactly the same as Q dash, because the order quantity is the same, so delivered quantity is the same. Some units of this Q dash in time period 7 is used to fulfill the back ordered demand, and the rest goes into the physical inventory. This is used to fulfill backlogs, or we use the term clear backlogs, and then the remaining is put into the physical inventory. So the positive values actually represents the physical inventory levels. With this notion of backlogs also comes this terminology of service levels, or this concept of service levels. We are taking the exact same behavior as we saw a minute ago, but now let us define something called as service levels. There are two popular ways in which we define the service. One is called as, we can compute the proportion of demand met as they occur. That is, there is no backlogs. Customer comes, he asks something, and we are immediately able to fulfill it. So how much fraction of demand we are able to fulfill in that manner, that is called as one measure of service. The other measure of service is proportion of order cycles with no stockouts. Let's take this one, the proportion of order cycles with no stockouts. In this case, we have 4 order cycles. 1 order cycle which goes from 0 to time 7, second order cycle, third order cycle, and fourth order cycle. At time 20 again we'll assume 10 more units has come. So out of these 4 order cycles, 1 order cycle had backlogs. So 3 order cycles did not have any backlogs. That means whenever there is customer demand, I was able to immediately fulfill, say during time period, say 9, 10, 11, any time period after 7, I was able to fulfill any customer demand that occurred. But in this first order cycle, we are not able to do that. So the proportion of order cycles with no stockouts is 3 by 4, which is 75%. Now, let's look at the first one, the proportion of demand met as they occur. Now, if you see, the demand is, just for this example, you can see that inventory level goes up to 10 and demand rate is constant. So that means in each period, and we have 4 cycles. So the total demand in this case is, total D or demand is 40 units, of which you can see in time period 5 to 7 about, let's take this as 4 units. So the total backlog was 4 units was backlog. So now we have the proportion of demand met as they occur would be 36 by 40, which is 90%. This is just a very simple illustrative example to compute service levels. Most often we'll encounter service levels when demand is stochastic. We will ignore the fact that you forgot to order and hence there are service levels. We'll assume demand is stochastic, hence we'll understand service levels better when we cover those topics. So in summary, we looked at several behavioral time graphs of inventory, hoping to visualize what happens to inventory dynamics. So, and we saw a classical sawtooth shaped behavior of inventory over time. Several notations and terminologies were introduced, such as order quantity, cycle length T or order cycle T, lead time L, back ordering, service levels, etc.